Okay, let's continue for discussion about section 3.6, that is the polarization of time-varying electrical field. Polarization, 极化, polarization is the characteristic that describes how the tip of a sinusoidal time-varying field vector at a point in space changes its position with time. In the case of waves, when we talk about polarization, we refer to the electrical field associated with the wave. Even though that we in an electromagnetic wave, we have both the electric and magnetic field, but when it comes to the field polarization, we usually refers to the direction of the electrical field. 以电场的振动方向为准。So, as the equation shown in the bottom of the slide, we see here is a description about the electrical field intensity. And we know the propagation direction is to either positive z or the negative z direction. However, there is another direction description about the electrical field intensity, that is the E field direction, which is in the x direction in this case. And as you can see, even though the time and position changes, and even though the magnitude of the electrical field becomes smaller or larger, or it can be a positive value or a negative value, nevertheless, the direction of the electrical field is always on the x direction, on the x-axis. So for these kinds of electrical field, we can refer to it as, this electrical field has a linear polarization, 线性的极化, linear polarization. And the polarization is in parallel with the x direction. 所以以这一个 equation 的描述来看的话，我们看到它是在电场是在 x 方向上面振动的，而且只有 x 方向上面振动的成分，没有其他方向，所以我们说它是一个线性极化，而它线性它的这个电场振动方向呢是落在 x 方向上面。那当然这是一个特别的例子。那我们今天会看到一些更 general 的一个 description。We can see more general description about electrical field intensities in this section. So the top figures plots the electrical field intensity description stated in the previous slide, that is the E field propagating in both positive and negative z direction. And the electrical field vibrating direction is on the x-axis. So as the plot suggests, the black arrow head, which indicates the magnitude and the direction of the electrical field, is aligned with the x-axis. So they are all located on the x-axis, and according to different position, the magnitude can be either positive or negative, and the magnitude can be large or small, or even have some zero crossing, according to the specified frequency. So according to the variation in space for the electrical field, you can also identify the wavelengths of the field. Then the plot below it, that is the plot B, shows the magnetic field intensity. And remember that how can we determine the expression for the magnetic field? As long as you know as long as you know the description about the electrical field intensity, you can use the cross product of propagating direction cross the E field and divide it by eta sub 0, which is the ratio between E and H field. And you end up with the magnetic field intensity description, as we have shown in section 3.5. So if the propagating direction is in the z direction, so z cross e, which is in the x direction, z cross x, end up with fields on the y direction. So as the figure suggests, you know, the magnetic field is also vibrating on a line, which happens to be the y direction in this case. So for a linearly polarized electrical field, the associated magnetic field also linearly polarized, which means it also stays in the same line. And there are another relationship between the electric and magnetic field vibrating direction is what? Is that they are perpendicular to each other, they are orthogonal to each other. 它们是一个正交的关系。所以我们一般在讲极化的时候，都是指电场的极化了。那假如电场是线性极化的话，那其实磁场也会是线性极化。但要注意的是，线性极化其实是一个蛮特别的 case， 特别的 case。但是在无线通讯里头呢，线性极化又特别的重要，又特别的重要。为什么 ？Why? Because let me see what do we have lines? Okay. So in this slide we have some other cases for electromagnetic wave polarization. As I already mentioned, linear polarization is a special case. Another special case is the so-called circular polarization, 圆极化. And however, there is another polarization which is the elliptical polarization, 椭圆极化. Elliptical polarization is the more general one. And you can say that both the linear polarization and circular polarization are special cases for the elliptical polarization. So the elliptical polarization can include the linear polarization as well as the circular polarization, which is, well, the more general case. And in fact, most of the electromagnetic wave you observe should be in the form of elliptical polarization. Okay. Nevertheless, we have already mentioned that linear polarization is more important toward wireless communication. Why? Because it's easier to generate linear polarization. So I don't know, have you ever noticed that if you have some wireless communication devices, and if the antenna of the wireless communication device is visible, 假如你这个行动通讯装置上面的天线是可以看到的话，你觉得那个天线通常你看到的天线长什么样子 ？Well, in most cases, it's a straight wire. It's a straight wire. Well, and in some of our previous discussions, the example, the antenna is usually represented as, for example, the most classical antenna we have in antenna textbook is the so-called dipole, which comes two, 什么是 pole 啊 ？pole 是一根的东西叫 pole 啦，所以 dipole 就是两根啦，所以意思说它指的是这个天线的上下两根，所以它称之为 dipole，所以这个叫做 dipole antenna，And well, but in fact, the most commonly seen antenna is the so-called monopole. 所以 pole 是一根东西嘛 ，mono 是一根，所以在 monopole antenna 里头，你看到的是一根，那为什么 monopole 比较常见 你只要去看一些通讯装置，比如说 walkie-talkie 啦，或者是你看那个周星驰那个年代的港片的时候，他们拿那个大哥大，是不是就是长这样一个方盒子，上面一根，那上面一根的话，你也看得出来那个叫什么天线嘛，OK， 所以 for wireless communication devices in the early days, the monopole, which is quite popular because they are easy to design, easy to integrate with the mobile device. Technically speaking, this part is refers to the monopole. However, the bottom half, the handheld devices, the handheld device, the bottom part of the phone is the other half of the antenna. So the two combined forms a dipole, effectively. And so the dipole or monopole configuration is relatively easier to design as long as what? As long as the length of the antenna with the device is about half wavelength. Then you can support the operation of the wireless communication device. So in the early day of mobile communication, I mean about 30 years ago, when the first generation of the mobile phone was developed, the frequency used that day is about 800 to 900 megahertz. 早期第一代的那个行动通讯哈。So what is the wavelength corresponding to this frequency? What is the wavelength at 1 gigahertz? 我喜欢问我的研究生了1 gigahertz 的波长是多少？3乘10的8次方除以10的9次方等于多少？0.3等于多少？30公分有没有？你们身上有没有什么东西是接近30公分的？有啊，你往下面看就有了。你的那个脚丫子大小就差不多30公分嘛，对不对？所以这一个尺寸是蛮好记的那当然，那个30公分其实是那个英国皇帝爱德华几世的那个脚丫子大小所以 1 foot 1英尺是用他的脚丫子大小来定的嘛那我好像29吧OK 跟我的身高比起来，我的脚丫子还算大的大部分人可能才26、27而已吧OK. But anyway, so as you look at the numbers for the mobile phone in the early days, its size is about the same order. So it's as long as you have some straight wires, you can use that to configure the antenna according to the size, according to the length of the wavelengths. And so from the perspective of transmitter, from the perspective of transmitting the electromagnetic wave, you need to have a transmitting antenna. How about the receiving antenna? Because in the wireless communication scenario, you need to have a transmitter and a receiver. And the receiving antenna should be what? Well, the general principle is your receiving antenna must have a polarization that is the same as the transmitting antenna. Okay? So let me explain this a little bit in detail. Say you have say If this is the transmitting antenna of our wireless communication application, so what happens with this transmitting antenna? As you can see from our previous slide in section 3.4 and 3.5, the generation of electromagnetic wave is due to the presence of time-varying electric current, J, right? So the current is going up and down in this antenna, in this transmitting antenna. What happens next? Due to the presence of currents going up and down, there will be electrical field going up and down as well. And what is the direction of the electrical field? Well, as we have seen in the previous slide, for the generation of plane wave, we know that the associated electrical field induced by the presence of vibrating current also goes up and down, The E field also goes up and down. However, the direction of the E field and the direction of the current J is what? Is of opposite direction. Why? The Lenz's law. The Lenz's law. All right. So as you can imagine, there is currents going up and down in this antenna. So it generates electromagnetic wave propagating outwards towards me over here and towards you as well. So if you have a receiving antenna like this, how should I position my receiving antenna? Should I position it upright like this or horizontal like this? Well, I need to orient my receiving antenna in an upright position. Why? Because the electrical field coming toward me is going up and down like this. So you need to have your antenna rod that is also in parallel with the electrical field, so that the free electron within this metal rod can go up and down due to the presence of electrical field, incoming electrical field. So the incoming electrical field will tell the free electron in this metal rod says, "Hi, come dance with me." Well, okay, goes up and down as that goes up and down together. So this is the so-called induced current in the receiving antenna, right? 所以当你的发射天线所产生的电场是上下震荡的时候，我们称之为垂直的线性极化。那你的接收天线也应该垂直摆放，这样子你接收天线里头的自由电子才能够感应到上下震荡的电场，也跟着上下震荡，形成所谓的感应电流。那这个感应电流就可以传达到你的接收机，来去当做你的接收的讯号。On the other hand, what happens if you orient your receiving antenna in a horizontal position so that it's perpendicular to the incoming electrical field? Well, the free electrons in this horizontally placed antenna still sense the urge of the electrical field to tell it goes up and down. Nevertheless, due to the geometry of this metal rod, which is placed horizontally, it cannot go up and down, and it cannot form the induced current. So even though that there is electrical field appears in this region, in this remote region, it cannot produce induced current, so that it cannot sense the energy or the signals coming from the remote side All right, so here is an important principle in wireless communication, that is, the transmitting and the receiving antenna needs to have the same polarization. If the transmitting antenna is linearly vertically polarized, then your receiving antenna should be vertically polarized as well. If you have a receiving antenna that is horizontally polarized, then we can claim that because the polarization does not match, so you won't be able to receive the incoming electrical field. So the one important principle that I have just explained is you need to have the same polarization for both the transmitting and receiving antenna to capture, to get the incoming electromagnetic wave. All right? So from this slide, it says on top of the linear polarization, there are another two polarizations that can be expressed mathematically. One is the circular polarization, and the other is elliptical polarization. In fact, in an example of in section 3.5, we have seen, okay, let me go, this one. In fact, for this example, 3.11, it's actually a circular polarization. It's actually a description of a circular polarization. Why? Because you see it has X component and a Y component, right? So the electrical field in this case has both X and Y components. And they are of the same frequency. You see the functions are in the form of omega t minus beta z. And you can see that they have the same omega and they have the same beta value. And another important thing about this description is the two components, the AS component and AY components, are different by 90 degrees. Their phase has a 90-degree difference. And this is one of the critical criterion you should have for circular polarization. That is, the phase of the two perpendicular components for two orthogonal components has a 90-degree phase difference, which is satisfied in this case. Another important criterion is the magnitude for the two orthogonal components should be the same. So as you can tell from this equation, the magnitude for the X component is 10, and it's 10 as well for the Y component. So in fact, this is a description for circularly polarized electromagnetic wave. All right? So because why this kind of description is referred to circular polarization? Let's check up in this way. Say if position Z is 0 and the time is 0 as well, so both T and Z are 0. So what is the variable within the sinusoidal function? The variable in the sinusoidal function are 0 for the two cases. And sine 0 is what? 0, yeah. Sine 0 is 0, cosine 0 is 1. So for at a position Z equal to 0 and at the time instance of T equal to 0, you have only Y components. And as the time progresses, suppose that you remain at the position of Z equal to 0, but the T is increased gradually. Then as the T increase and the variable omega T minus beta Z equals to pi over 4 or 90 degree, then sine 90 degree is 1 and cosine 90 degree is 0. So at the following moment, the electrical field has only the x component, positive x component. So from t equal to 0 to t equal to pi over 4, you have the direction of the electrical field is rotated from positive y direction toward positive x direction. And if you keep tracking the variation of the field, you will see that it goes to the minus y direction, then goes to the minus x direction. So it rotates from, in this order, positive y, positive x, negative y, negative x. And because the magnitude of the both components are 10, so you can imagine as it rotates, and you know that this is a sine, they are both sine functions, so sine square plus cosine square is what? Is 1. So the magnitude of the total field remain as 1, remain as a constant. So if you trace the direction of the electrical field at the different moments, it's kind of following a circular locus, 一个圆形的一个弧线，圆线circular locus for this description. So therefore, this kind of field is, this kind of polarization is, this kind of field is referred to as the circularly polarized, 原极化的场. All right. So as I already demonstrated in the previous example, for circular polarization, the magnitude of the electrical field remains as a constant. So it rotates with a consistent magnitude while the direction, is changing, like follows a circular locus, circular path. On the other hand, if the magnitude and the direction of the electric field varies, if the electrical field varies in both the direction and the magnitude, then it should, the end, the tips of the electrical field can follow an elliptical locus, like the one drawn in the slide. So it's referred to as elliptically polarized or elliptical polarization. So elliptical polarization is characterized by both magnitude and direction of the field changing with time. So here we have the elliptical polarization, circular polarization, and linear polarization. So let's consider two components and discuss the different cases. So if the two components, sinusoidally time-varying vectors have arbitrary amplitude but are in phase or in phase opposition, as for example like this. So what are the difference between 3.102A and 3.102 and B? Well, the first difference is their direction. One is in the x direction, the other is in y direction. The similarity between the two is they are in phase. So you see the variable in the function, in the sinusoidal function are both omega t plus phi. They are the same. So they change simultaneously. They are in phase, so-called in phase. Their magnitude can be different. Say F1 comes with the magnitude of F1, F2 comes the magnitude of F2, and there are no guarantee of F1 equals to F2 or different. So they can be different, but they can remain a constant ratio. So the sum vector is linearly for this case, we can see that it's, even though it has two components, but this is still a linearly polarized electromagnetic wave. So you need to figure out why this, the addition of F1 and F2, well, of course, if you look at F1 alone, it's linearly polarized. F2 alone is linearly polarized, but the combination of two still adds up as a linearly polarization. 所以我们今天这一页哈，以及下面的几个例子哈，你要去看懂为什么它会是属于线性极化或者是原极化哈。那这边的话，你会看到 F1 component 是线性极化 ，F2 component 其实也是线性极化，而它们加起来之后还是线性极化哈。那当然我们等一下会秀一些原极化的 case， 你要去看一下它们的差别，为什么加起来这个加起来是线性极化，那个加起来是原极化啊？差别在哪里，就要去分辨得出来。Alright, so the sum of the two components still add up as a linearly polarized. Why? Because they are very in phase. The two functions are what? Are in phase. Okay, they're very at the same rate as the time changes. And as you can see here, it's a linearly polarized with screen angle. It's slightly linearly polarized. It's not aligned with the X position nor with the y direction. But it's aligned with a slanted path. And the angle of the path is alpha, is referred to as alpha. So it's a slanted linear polarization. And alpha can be determined by the arctangent. 这有没有看懂？这个叫做 arctangent。计算机会不会按？要会按。OK， 好，相信各位会了哈。所以 fx over fy over fx, arctangent of fy over x shall help you derive the angle or between the two vectors. And so in conclusion, because the two vectors are added up in phase, so the addition of two linear polarizations still adds up as a linear polarization. It just happens to vibrate on a slanted path. So this is the an illustration of the field of F1 plus F2. So F1 is in the y-x direction, F2 is in the y direction. The addition of the two is the vector F. But as you can see, as time changes, the F vector is going forward and backward in this slanted path. So as long as the two vectors are added up in phase, it's still a linear polarization. So the sum vector of any number of linearly polarized vectors have different directions and amplitude, but in phase is still a linearly polarized vector. Then here is another example. So look at this example. F1 and F2 are perpendicular. As you can see here, one is in the x direction, the other is in the y direction. They have the same frequency. So you see the variable are omega t plus phi for the two cases. Nevertheless, they are different by 90 degrees. The two functions are different by 90 degrees. So you see one is cosine function and the other is sine function. And another important criteria for this case feature, another important characteristic of this example is that the magnitude of F1 and F2 are the same, which are both F sub 0. They are both sub 0. So the x component and y component are the same for this case. So to determine the polarization of the sum vector of F equals to F1 plus F2, we know that the magnitude of F, which can be given by the absolute value of the sum of the two F1 and F2, always equal to 0. Why? Because one varies in the cosine form and the other varies with sine form, and they are perpendicular to each other. So the magnitude of this addition will be the square root of the square sum of the two components, which happens to be f sub 0 for all time. So we know that the magnitude of the sum vectors remains as a constant, which is f sub 0, and the angle of the sum vector, which is by definition is calculated as the arctangent of y components over x component. So you can substitute F2 and F1 into this equation, and you end up with omega t, because arctangent, this function tangent function, and here is the arctangent function. So you end up with omega t plus phi. So what is the significance of this result? It says that the tip, the direction alpha varies with time, which in the form of omega t plus phi. So as you know, because omega is 2 pi over lambda, so 是吗？不是 omega 是 2 pi over f。 2 pi f. No, omega is 2 pi f. Okay. So it's periodic. So it's a rotating. So well, so it's probably similar to identify these characteristics from the plot. So if you trace the direction of the sum vector f, you can see that it's rotating in this fashion, clockwise, rotating in the clockwise fashion. And omega happens to be the angular frequency, which is referred to as 角速度，角频率吧，我讲错了。我写错了，对不起，不是角速度，应该是叫角频。omega 对啊 ，angular frequency 角频率才对啊，为什么会写成角速度？角频率哦。不过差不多意思啊，单位时间的那个进度的变换量啊，都可以了 ，OK， 好。All right, so. Here we see a true linearly polarization. If the two linearly polarization components have the same magnitude and differ by 90 degrees, then the addition of the two, and they are perpendicularly polarized, then the addition of the two can form a circularly polarized wave. That's an example for a composition of circular polarization, which means the direction of the total E field will trace a circular path. That is, the magnitude remains the same as it rotates, and the rotating speed is comply with the specified angular frequency. So if two linear polarized vectors satisfy the three conditions, as we already checked in the previous example, that is equal amplitudes, perpendicular in direction, and phase difference by 90 degrees, then the sum vector of the two linearly polarized waves can form a circularly polarized wave. For the general case, if one or some of the conditions above are not satisfied, then you always end up the so-called elliptically polarized. That means the orientation of the total E field is still changing as the time progresses, and its magnitude can vary as the time changes. So, as a conclusion, both linear polarization and circular polarization are special cases for the general elliptical polarization. All right? 所以我们今天的 3.6 里头所看到的这一个所介绍的，其实就3种极化：椭圆极化、圆极化跟线性极化。而椭圆极化跟线性极化跟圆极化都可以被视为是椭圆极化的一个特例特例。那我看一下有没有 ，sorry。所以椭圆极化是通例了general case， 而圆极化跟线性极化是椭圆极化的特例 special case。And on the slide is an example for elliptical polarization. So let's check. It has two components. So F1 is in the x direction, F2 is in the y direction. So they are perpendicular to each other. So it meets one of the three conditions for circular polarization. However, the ratio of the magnitude is A and B, which for this case is 40 and 60, which means they are not of the same magnitude. So from this description, we can determine that the addition of F1 and F2 cannot form circular polarization. So it got to be the so-called elliptical polarization. Another condition is the phase difference of the two, which can be determined by phi and theta angle here. We see F1 is cosine omega t plus phi, and F2 is cosine omega t plus theta. So the value of phi and theta will also be an important criterion. So if phi is equals to theta, so then they are in phase, then we can say that they are they can form linear polarization. And if phi and theta are different by 90 degrees, then they have the chance to form the so-called circular polarization. And from the problem description, we know that phi is 60 degrees and theta is 105 degrees, so the difference is 45 degrees, which is neither 0 nor 90 degrees. So it cannot satisfy the three conditions for circular polarization. So because the phase difference is not 90 degrees, so of course we can say it's elliptical polarization. So the plot shown here is following the trace formed by the tips of the sum vector, F1 plus F2. So as you can see, at a certain time instant, you have magnitude of 40 over here and 60 over here. And it form, because the difference, they form an elliptical traces. And for an elliptical trace, there is another, there are some other important okay. For an ellipse, there are two parameters. That is, there are major axis and the minor axis.这中文是什么 ？Major axis 跟 minor axis。椭圆的两个轴椭圆的两个轴的大小比例。其实我也不知道，我中文也不记得。OK， 那就直接记英文了 ，major axis 跟 minor axis。So the ratio of major axis over minor axis is referred to as the axial ratio. 轴比。So can you tell me what is the axial ratio requirement for a circularly polarized wave? 假如你是原极化的话，它的 axial ratio 是多少？我要原极化它的 major axis 跟 minor axis 有没有差？没有嘛，一样嘛。Okay, great. So for circular polarization, CP 哈。CP 的话，它的 axial ratio 会等于1。那 how about a linear polarization? What is linear polarization? You can imagine that linear polarization is elliptical polarization with a very large major axis to minor axis ratio. So for linear polarization, it's axial ratio approaches to infinity. So anything for any axial ratio in between, they are the so-called elliptical polarization. So anything in between is elliptical polarization. So there's another ways to determine the property of wave polarization. All right, and so here's the example of polarization. 有没有人在玩那个摄影的？有没有人在玩照相的、摄影的？假如你有那个什么高级的什么单眼摄影相机的话，那有没有人玩过？有没有在玩的？当然要有点钱啊。OK， 好，没玩过啊，但我听说过就是说，假如你在玩那个假如你用单眼相机的话，比如说你要去拍什么早上的湖景还是什么，有时候你会加一个偏光镜。那个偏光镜加上去之后，你的相片会变得，对我这种凡人来讲，我可能看不出什么差别吧。他对他们来讲说是有差的。为什么？因为，换个例子来讲好了。剩3分钟。有没有去过六福村啊？有吗？你们小时候高中还是国中毕业旅行一定会去的嘛？六福村的。那个六福村里头就有几十年前就有一个什么3D 电影院，对不对？当然那个3D 电影院跟你现在已经好像没什么3D 电影了，对不对？除了那个《阿凡达》以外嘛，对不对？那个《阿凡达》给你那个3D 眼镜又大又重嘛，对不对？那个原理我们有空再说好了。那你去六福村的那个3D 电影院看的那个，它也一样会给你一个电影，对不对？给你一个眼镜嘛，对不对？那看起来是透明镜片，对不对？那我不晓得你有没有跟你的那个隔壁的朋友或女朋友借他的那个镜片来玩一下哈？你应该不会一个人去六福村吧？听起来有点寂寞，对不对？傻逼戏 ，OK 啊。所以你只要拿两个那个眼镜把左眼跟右眼叠在一起，你会发现一件什么事？它变成黑色的啊！为什么？因为它那个六福村那种传统那种戏院的那个眼镜，它其实就是用2个偏光镜片，一个是垂直极化，一个是水平极化。所以因为你要看3D 影像，其实就是左眼看左眼该看的，右眼看右眼该看的。所以你只要把眼镜拿下来，然后裸视去看的话，你会看到那个画面是糊的嘛，对不对？因为它把左眼跟该看的跟右眼该看的叠在一起，所以只要你把那个3D 眼镜戴上去的话，你就完成了所谓的 polarization division 就是用极化来去分解出2个channel，然后这2个channel分别是左眼跟右眼该看的。所以，假如你把那个左眼跟右眼的那个晶片叠在一起的话，那就不透光嘛，因为等于2个垂直的那个。那至于阿凡达那种贵的，不小心一屁股坐上去，你可能要赔戏院3000块的那种镜子，那个镜片它是主动式的，它是 time division。我们可以把它想象成是时间上面的多工，也就是说那个。你在看那个阿凡达的那个眼镜，其实它是随着影片的播放，一下子遮你的左眼，一下子遮你的右眼，所以那个眼镜上面你会注意到，它其实还有第3只眼，有没有？除了左边、右边以外，中间还有个小窗，那个小窗是一个什么？那个 infrared 的一个 sensor， 那是对着前面从荧幕过来的那个。synchronization 的那个 signal 做同步的讯号，所以你只要把那个小窗盖住的话，你一样看不到。阿凡达3是不是快上了可能明年就上了吧OK， 所以下次去的时候可以玩玩看所以你只要把那个遮到之后，那个3D 效果就不见了，因为它没有那个 synchronization 的那个 signal， 它就不知道它其实是用易经啦。帮你一下子遮左眼，一下子遮右眼，一下遮左眼，一下遮右眼，所以这个是不同的那个3D 的那个做法，好吧？我们先休息一下吧。对，那个你在六福村里头，你只看那个影片只有10分钟嘛，所以你会坐直直的看嘛，对不对？你只要在那个黑黑的地方2个小时。你的头可能不小心就歪过去了嘛，对不对？OK， 我们继续OK, so an example in which polarization is relevant in the reception of radio waves, as I already described, there's one principle for wireless communication, that is, the transmitting antenna and the receiving antenna should have the same polarization, so that it can be you can receive the transmitted signal effectively. And of course, you may see, you may ask one question. Of course, you know that if the transmitting antenna is vertically polarized, so your receiving antenna is supposed to be vertically polarized as well, to fully take the advantage of incoming electromagnetic wave. If you orient your receiving antenna horizontally, then you got nothing, even though there is E field in presence at this position. How about I rotate my receiving antenna by 45 degrees? So if I rotate my receiving antenna by 45 degrees, what happens to the reception? 你们听过一句话叫投降输一半对，假如你把天线歪45度的话，你就是剩一半because you can imagine that the antenna can a 45 degrees slanted antenna can be decomposed into a vertical one and a horizontal one. So if you do not, if the polarization of the 2 linear antenna does not match, then it depends on the projection. It depends on the projection, amount of projection, to determine how much you can receive from the orientation. So if it is if the receiving antenna is slanted by 45 degrees, then you got half of the incoming power. All right? And so this statement says that if the polarization are the same, then it's more effective. Otherwise, if the polarization does not match, then you may have some of the incoming energy. If the 2 polarizations are perpendicular, well, then you got nothing, right? And the same thing is applicable for other polarization, for circular polarization. So for circular polarization, there are two kinds of circular polarization. One is the right-hand circular polarization, and the other is left-hand circular polarization, which are abbreviated as RCP for right-hand circular polarization, and LCP for left-hand one. And what is the difference? Well, let me follow the description in the slides. All right. Okay. The convention of right hand and left hand is determined by the rotating tip of the electrical field. The tip of the field vector of a circularly polarized wave rotates with time in the clockwise sense, as seen looking along the direction of propagation of the wave. The wave is said to be right-hand circularly polarized, right? And a footnote for this description is you look into the direction of propagation. So suppose you have a wave, say x, y, z, okay? If this is the coordinate x, y, and z, z is what? This is right hand. Z is in this direction, all right? So if the wave is going to the positive z direction, so you should look at the wave along to its propagating direction 所以就像我们这边footnote写的，从屁股往前看往波传播的方向看过去So if at the time instant of t equal to 0, if the electrical wave is pointing to the positive x direction at t equal to 0, and it becomes pointing toward the positive y direction for t equals to pi over 4. That is 90 degrees. So now the tip is rotating in a clockwise sense. Then you can follow up the tip rotation with the right hand, where your thumb is pointing toward the wave propagating direction. Then this is referred to as the RCP, right-hand circular polarization. So the other case is relatively simple. If at t equal to 0, it's pointing upward as the positive x direction, and it rotates to negative y direction at t equals to pi over 4. So from your perspective, the field is rotating in a counterclockwise sense. Then it can be, the tip rotation can be followed by your left hand screw, 左手来旋转 left hand screw. Then this is referred to as the left hand circular polarization. So here are some tips for you to determine the polarization of circular polarization and elliptical polarization as well. So similar consideration holds for elliptically polarized wave. And here's the example. As I already mentioned, example 3.11 is actually a description for circular polarization. So here we can take a further look at the description for the E field in example 3.11. The two components of E are equal in amplitude. As you can see here, they are both 10 in the magnitude. They are perpendicular. So one is pointing to the x direction, the other is pointing to the y direction, and out of phase by 90 degrees. So you can see that one is sine function and the other is cosine function, where they have the same variable, the time and spatial variable for the two components. So therefore, it's referred to as circular. It can be determined that this field description is valid for a circularly polarized wave. So they need to have a 90-degree phase difference. The two components need to be perpendicular, and the two components must have the same magnitude. So their addition, the sum of the two linearly polarized waves of these quantities can form a circularly polarization. To determine if the polarization is right-hand or left-handed, we look at the electrical field vector in the z equals to 0 plane. So we set z equal to 0 to start. Well, this make it a little bit easier to determine. And look at the two time value. One is t equal to 0. The other is this, which happens to be pi over 2. pi over 2 是90度啊，我刚才写错了，不是pi over 4，是pi over 2才对哦。pi over 4是45度啊，我黑板上面写错了哈，帮我订正一下。So at t equal to omega t equal to 0, which is 0 degree, it's pointing to the y direction. And when the omega t value goes up to pi over 2, that is 90 degree, it's pointing upward. So as I demonstrated on the example in the blackboard, if you look at to the direction of wave propagation, which is in the positive z direction, then as the time varies from t equal to 0 to t equals to 1 over 6 to the times 10 to the minus a, the locus of the tip of the electrical field can be followed with a left hand. So we can determine that this example belongs to the LCP, left-hand circular polarization. All right, so let's move on to section 3.7, which involves the power flow and energy storage of electromagnetic wave. So let me remind you as you can imagine, what is the objective of an electromagnetic wave? 电磁波的目的，它的目标是什么？这当然你可以说大自然没有什么目的或目标嘛，它就是这个样子了哈。但从我们的应用啊，比如说无线通讯啊，或者是无线传能的角度来想，电磁波能够达到什么样的目标？达到什么样的目的？传递能量。因为说我们要传递能量，传递讯号，讯号也是couple 在讯号也是 couple 在能量上面的嘛。所以我们可以认定的一件事，或者说我们觉得为真的一件事情，就是电磁波的传递的目的是要去 deliver signal or deliver energy. So from this perspective, we shall look at the energy or the power involved in the propagation of electromagnetic wave. So as the electromagnetic wave propagates, it delivers energy, it delivers signal. For example, the very reason that we can have life on Earth is because what? Because the energy provided by the sun. There's at least for the life on Earth, the energy input from the sun is very crucial, very critical. All right. So let's begin with our some scenarios that we already discussed. For surface currents flowing in the negative x direction, that is the example we have in section 3.4, we have an infinitely large surface current going up and down in the x direction. And we know that when the current is going down, they shall produce an electrical field going up. Well, well, actually, the direct product of electrical field is not the direct product of the presence of current. 我要强调的是，你这边再想一下哈，这个朝上的感应电场不是直接由电流产生的哦，电流的直接产生是什么？其实是磁场，其实磁场。那假如你是静电流的话，你就只有磁场而已。但因为我们这边的电流是时变电流，所以它的电流会忽大忽小，忽上忽下。所以它所对应到的磁场也是忽大忽小，忽上忽小，应该不是忽上忽下，忽左旋忽右旋嘛，因为你用那个右手定则来去看，安培右手来去看。那我们要用到的是法拉利定律 ，OK， 是法拉利定律吗？对，法拉利定律，对。那因为这个电流是时变的，所以那个磁场是时变的。那因为磁场是时变的，所以根据法拉利定律，它就会产生空间中的电场变化。而这个电场方向跟你的那个电流又是一个垂直的关系，所以你得到一个朝上的感应电场，朝上的一个电场，而这个电场的产生，根据冷次定律是需要去对抗因为电流所产生的磁场变化，因为电流所产生的磁场变化，所以你的电场是要去对抗它的，那结果是你这边所看到的电场跟电流方向是相反，所以代表什么？代表你这个电流必须要做功，它必须要耗费能量才能够产生这个电场，所以在这一个电流转换为电场跟磁场的过程当中，它其实是一个能量形式的转换，把电压电流的能量，因为你电流要由下往上流或由上往下流，那就表示什么？上面跟下面之间有一个电位差，所以它原本的能量形式是 V 跟 I， 所以是电压电流，所以它是电能啦，只是说它是以电压跟电流的形式在这个机制当中，但是透过这个上下振动的这一个电流，它就转换成往前跟往后的电场跟磁场的电磁波，所以这个电流的变动其实就是一个能量形式的转换，从电压电流转换成电场磁场。OK， 电压电流是局限在这一个局限在那个 source 那个地方的，但是你的电场磁场的能量就会怎样往前跟往后传播。而我们之前的例子也告诉你，你有多少能量往前传播，有多少能量往后传播。在一个相对简单的环境里头，那刚好就比如说是在我们的教室里头，中间有一堵电流墙，那么就一半的能量电磁波是往左边传的，一半往右边传的嘛。所以假如几何结构关系简单的话呢，那它那个 power 就是平均的分布了。那当然实际上你的传播环境是会比较复杂一点的那就再说吧再看你的边界条件来去决定。Alright, so from this description, we know that the generation of electromagnetic wave is due to the is originated from a conversion of energy from energy type. So you convert the electrical energy in the form of electrical voltage and electrical currents into the energy in the form of electromagnetic wave, which can be represented by electric and magnetic field. So here are some plots that we have already seen. It depicts the time variation of electromagnetic wave. So you can see that in the middle is your current source. So as the current direction varies as the time progresses, the field produced in early times will propagate further and further. So that's the reason why today, when you look at the sky, if you see the star series, 猎户星嘛，是猎户星吗？猎户星做的什么？天狼星啊 ，OK。If you look at the sky of Sirius, you know this was the light produced by the sun at a far distance about 4.7 years 这个，所以天狼星距离我们5光年嘛所以你现在看到的天狼星的光是5年前的，你现在看到太阳光是8分钟前的嘛，对不对？Alright, so let's consider. So here in following slide, we will attempt to calculate the amount of energy in the form of electrical field and magnetic field stored in the space. So let's continue a rectangular area of length delta x and width delta y. So as the plot shows, you have a rectangular region on the xy plane with width of delta y and length delta x. Since the current density on the z equal to 0 plane is J sub S0 times cosine omega t, the charge crossing the width delta y in the time dt is dq equals to J sub S0 times delta y times cosine omega t times dt. So this is the the amount of charge appear in a unit time, the q over dt, because what? This comes with the relationship of current equals to dq over dt, and this is the width times J, okay, and this is delta y times the J sub blah 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 over here, okay. And so of course you can like this. And if you times both sides with E, the electrical field intensity, the E times the Q, you can have the electromotive force. 感应电动势F 等于 QE 嘛F equals to Q times E. So here you have this expression. And F is what? Is force. Right? It's force. However, and the other parameter associated with force is what? W, the work. W equals to what? W 等于什么 ？W 等于 Fs 啦。So S is the distance. Force times distance equals to work. So at a unit time, the work dW equals to the force, which is in the x direction, times the distance traveled by those charges. So goes back to this slide. So at a specific time period, the charges move from here to here. All right. So it's the distance traveled by the charge is the delta x. So we can put delta x into the equation as this. So the dW, not omega, dW, no, the work, equals to J sub S0 times Ex times cosine omega t dt delta x delta y. And this is the work, and if you divide the work by time as the W over dt, you get what? You get power. No, 功率, power. So you have equation 3.109, that is the current density Js sub S0 times the electrical field at that position, that is Ex, times the time variant function of cosine omega t times the area delta x delta y. You have the power, the power of the of that region on the current sheet. And recording that Ex is related to the current source, which is eta sub 0 times J sub S0 over 2 times cosine omega t, as we have derived in section 3.4. So you can replace Ex with this as this. So you can see that the work, no, not the work, the power delivered by the current source in this area, delta x, delta y, is this, which is proportional to the amount of current density, J sub S0, and is proportional to the square of cosine omega t function. And of course, it's proportional to the area size, delta x times delta y. So here is the power delivered by a specific region on that current sheet. So the power delivered by the current source shall be transformed into energy stored in electric and magnetic field, which propagates toward the front and back of the current sheet. So far, we have calculated one thing, that is the power delivered by the current source. Then we will look at the same quantity, the power, in terms of electric and magnetic field. All right? So we'll look at this relationship again from the perspective of E and H field. But before we're doing that, we notice that the product, the cross product of E cross H equals to what kind of a unit? So let's take a look at this. The quantity for E is what? Is newtons over coulomb. Okay. Well, to tell the truth, I cannot remember this relationship. 牛顿 per coulomb， 电场是牛顿 per coulomb， 磁场是安培 per meter， 好吧？然后你的电场是怎么记的？电压 per meter 嘛，磁场嘞，安培 per meter 嘛，所以它们两者相除就是 voltage per 安培，所以等于电阻欧姆嘛，OK， 不过没关系啊，有不同的方式讲了这边你自己看一下吧So if you follow the units for E and H field like this, you ended up with this thing so that you can cancel out the coulombs and you have composition like this. Well, anyway, the end product is watts over meter to the square. So that's the unit area, the power in a unit area, right? So it's watts per meter to the square, which is the same as the units for this case, which is calculated in terms of the current density, the current density in the current source region. So the product of E cross H has the same unit as the per unit area power delivered by the current source. And these things are also referred to as power density. 单位面积的功率叫做 power density 或者说是功率密度所以我们等一下其实会试着去计算 E cross H 的结果。而 E cross H 的结果在电磁学里头其实还有一个专有名称叫做 Poynting vector。我不知道有没有听过以前没听过，现在就听过了So P is referred to as the Poynting vector. And is defined as the cross product of E cross H. So is Poynting vector a scalar or a vector? vector, of course. Otherwise, it's referred to as pointing vector. And what is the direction of pointing vector? It's the direction of power delivery. So it's the direction of power propagating direction. So E cross H is also which direction is E cross H? E cross H is the direction, refers to the direction of wave propagating direction. So you can think of propagating electromagnetic wave is a means to deliver energy in the form of electric and magnetic field. So that's the reason why the energy originating from the sun can propagate through the space to the surface of Earth, because it uses the form of electromagnetic wave to reach to a remote location. 所以不管是太阳能、太阳光，或者是我们无线通讯的那个电磁波，都是借由电场跟磁场的形式，把能量从甲地传送到乙地嘛，这一个传送的能量的单位就可以用 pointing vector 来代表，而 pointing vector 实际上它的单位是 watt per meter square， 也就是我们刚刚所看到的功率密度。In particular, the pointing vector P is the so-called instantaneous power. Instantaneous 瞬间的瞬间的。在我们在讲电磁学的时候我们会有所谓的 we have the instantaneous power and the so-called time average power. Time average power and the instantaneous power. Instantaneous power just varies with time, so it's the power at the very moment. And the so-called time average power is more meaningful for sinusoidal signal. So if the signal you have belongs to a specific frequency, then it becomes more meaningful to describe the energy delivered through this wave in terms of the time average power, and which is valid for most cases of wireless communication, because modern day wireless communication are usually facilitated in terms of a carrier frequency. 所谓的 carrier frequency 就是我们在讲无线通讯中的所谓的载波频率了也就是说你把讯号你要传递的讯号把它加载到一个特定的传播频率，比如说我刚刚讲的那个第一代的那个类比的那个行动通讯电话，它用的是800还是900 MHz 的讯号，所以那个900 MHz 的讯号就是所谓的 carrier frequency。All right, so the interpretation because pointing vector is the so-called power density. So to find out the total power, you need to do a surface integral. So you see, here's another expression that is the closed surface integral of E cross H dot ds. What is the meaning of this expression? Suppose you have a dipole, as I already described, and we know that due to the presence of vibrating currents on the dipole, it shall produce E and H field in its neighborhood, and they shall propagate outward and deliver energies to remote places in the form of electric and magnetic field, which is also in the form of pointing vector. So if you find out, if you define a closed surface that is enclosing the whole antenna, whole dipole antenna, and do the calculation of closed surface integral of the Poynting vector, which is the cross product of H and E, you can calculate the power emanating from this closed surface. So this integral, this surface integral, represents the power emanating from specific region. So if you have been interested in 你有没有听过戴森球？有没有？假如你有在听那些 YouTube 说书人的哈 ，OK， 那个是什么？戴森球理论的是理论嘛？假说啦哈，也就是说，假如说一个文明能够做出戴森球的话，好像就要不知道1级还是2级文明嘛，哈，也就是说什么？它能够运用整个，像人类的话，其实还没有办法运用完整的地球上面能量啊，我们可以使用部分啊，算是一大部分了哈。但只要你想要跨出太阳系、征服银河系的话，哈，那你要想办法能够运用更多的能量。那其中一种方式就是，你在太阳周围建造一个戴森球啊。那事实上就是 you build a sphere that encloses your power source so that you can intercept all the power available from this power source. Okay. So here's example 3.14, distance variation of fields far from a physical antenna. So in this example, we like to calculate the power emanating from an antenna. Assume that the observation plane is very far away from the source, so that the electromagnetic wave approximates as a uniform plane wave. Then the calculation can be simplified. And what we like to calculate is the Poynting vector, because Poynting vector suggests is the same as the power density. So with the surface integral of the power Poynting vector, you can get the power from this space. And we know that the Poynting vector is the magnitude of the Poynting vector is inversely proportional to the distance to the antenna. Okay, so how to interpret this statement? 有没有吹过气球啊？本过给鬼啊不？本给鬼啊，那个结果是什么哈？那个气球就是那么大嘛，对不对啊？你吹的越大，气球就越大哈。那怎么样呢？那个气球皮就越薄，对不对？那你只要继续吹的话，总有一天它会爆掉嘛，对不对啊？所以不管你那个气球吹的大还是小，它的球皮的总质量是一样的嘛，对不对？所以假如你的气球吹的越大，那个球皮的那个厚度就会怎么样？跟半径平方成反比嘛，对不对？越大的话，你那个气球就越薄啊。所以从能量的观点来看我用两个球去包那个天线，它包覆的总能量，不管是大球还是小球，它包到的总能量是哪个多哪个少？一样的嘛，就跟吹气球一样嘛，所以它意思是什么？意思是说这里的 Poynting vector 跟这里的 Poynting vector 是成一个距离反比的关系嘛，因为我们这里头因为是包覆它，所以它是一个面积，所以面积跟距离的平方成反比So the total power is the same, therefore the power density, which is the Poynting vector, is inversely proportional to the distance from the observation sphere to the source antenna, assuming that the wave is propagated like like a spherical surface, like a sphere, in a spherical. So here we will introduce another concept in geometry, that is the steradian. 有没有听过 steradian？ radian 是那个进度嘛，中文叫进度嘛，也就是以派来去代表的。那 steradian 呢 ？STER 吧。steradian is 我们中文大概叫立体角吧，是不是？好 ，OK。So我相信你应该可以做得到这一个积分哦。So if you taking the surface integral of a constant in a spherical space, which is theta from 0 to pi and phi from 0 to 2 pi, which equals to sine theta d theta d phi. Okay, you should verify by yourself what is the product, what is the integral of this thing. It's 4 pi. So 4 pi is the total steradian of a spherical space. 对于一个球面来讲，它的球面积角，你用立体角来去判定的话，是4派的大小。So no matter the distance is, no matter the observation distance is, the spherical area enclosed by a spherical surface is 4 pi steradian. So if you remain for a large or for either a large or a small spherical surface, as long as the steradian is the same for the two cases, then the total power enclosed in this region should be the same, which means the power density, the Poynting vector, should be inversely proportional to the square of the distance, all right? And so because the power density is inversely proportional to the square of the distance, then the electric and magnetic field are inversely proportional to the distance. 因为 Poynting vector 是电场乘上磁场的嘛，对不对？所以既然 Poynting vector 是跟距离平方成反比，所以电场跟磁场呢就是跟距离成反比。Okay, and this kind of dilation, 稀释我们称 dilation. This kind of dilation is referred to as free space reduction, which cannot be changed using engineering measures. That's the way it is. That's the way it is. 就像 Mandalorian 讲的 this is the way. How electromagnetic wave propagates. So the so-called free space reduction is there as the wave propagates in space. And that's the reason why the idea of our wireless powering is我不知道你有没有听过有之前在前十几年前有这样子那个我们生活的空间电磁波无所不在嘛，对不对？我们生活的空间里头充斥着电磁波嘛，对不对？你的身边一定有那个 FM 的讯号，还有手机的讯号嘛，对不对？还有基地台的讯号嘛，对不对？我们讲能够用这些电磁讯号，然后把它转变成能量的话，搞不好就可以帮你的 iPhone 充电嘛，对不对？当然是不太实际啦，为什么？因为那个基地台的发射功率也不过是20瓦，跟那个传统的那个日光灯管差不多，比你一颗那个百叶灯泡还要小，所以你与其要用那个背景电磁波来帮你的 iPhone 充电，还不如拿一块那个大的太阳能板伸到那个窗户外面收太阳能，还比较有效率，OK。 应该可以啦。假如你够厚颜无耻，拿一块大太阳能板出去的话 ，OK。All right, so but anyway, even though that the idea of wireless powering is not likely, but it still provides enough power, enough energy to facilitate communication, wireless communication, because we only need a very small amount of energy to carry or to deliver information wirelessly, all right? So, of course, this thing should be considered in terms of the idea of power density is critical. So, returning to the electromagnetic wave on current sheet, we can consider the region that is delta x, delta y, and we can calculate the Poynting vector associated with a specific region in space. So the Poynting vector, if you have an if you have a plane wave with E field in the x direction, y field, h field in the y direction, and as specified in the example explained in section 3.4, the Poynting vector P can be calculated as PZ, which is the product of EX and HY. And substitute the solution for EX and HY in the previous example. You have eta sub 0 times J sub S0 to the square over 4, because it's over 2 for the 2 case, times cosine to the square of omega t minus beta z. So this is the Poynting vector calculated from the E and H field. And if you draw the result graphically like this, so the horizontal axis is your z-axis, the difference in space, and the vertical axis is the magnitude of the Poynting vector. You see what is the significance of this result? Well, it varies like a sinusoidal function. I mean, like a sinusoidal. Is that a sinusoidal function? No, it's varies as cosine to the square. So it's not a sinusoidal function. It's the square of a sinusoidal function. And because it's the square of a sinusoidal function, you see the minimum value of the Poynting vector is what? It's 0. And it's all positive. So which means the power is always delivered to the right. Because it's a positive value, so it always goes to the positive direction. However, the amount of the Poynting vector can be large or small at a different position. So what is the significance of this result? It tells you that the power, the energy is not homogeneously displaced in the space. It's like well, the power as the electromagnetic wave propagates, the power can be imagined as 一谱一谱的啊，所以不是那个你在电动玩具里头打的那个能量光束不是这样子，一条啊那搓搓啊那它事实上电磁波的能量在空间中传播的时候，它是一谱一谱的，那个一谱一谱的那个间距是这个 zero crossing 是半个波长。OK， 所以根据你的频率那个能量在空间是这样子一球一球的所以这个是这边所看到的一个结果所以 according to the graph, the instantaneous Poynting vector is not the same, all right? Now, so for a specific place like this, for this region, you can see that there are more power delivered to the Y while less power is supplied from this space, which means there are some energy stored in this space. But instantaneously, at this very moment, there are, for example, there may be more energy coming into this space and less coming out. But from an average sense, if you observe with enough time, you